KMT, or the kinetic molecular theory, is going to give us a lot of information that will prepare us for the gas laws. And what the kinetic molecular theory states is that matter is made of particles that are constantly in motion, and the amount of motion is proportional to the temperature. Now, temperature is an average measure of the average kinetic energy. So even those solid things that we see out there where we can't see any of the atoms that are moving around, they are actually moving. Now solids are moving just a little bit, but they are still moving. If I were to put a drop or two of food dye into a glass of water, without stirring it, eventually all of that dye is going to be evenly dispersed throughout that container of water just because those liquid molecules are constantly moving around. So this again is going to get us into the ideal gases. And an ideal gas obey gas laws, which we'll talk about in a couple of days, at all temperatures and pressures. They do not liquefy or solidify. There's no attraction between the particles. The particles that are in an ideal gas have no volume, but they don't exist. Okay, ideal because in an ideal world they would, but we don't have an ideal world. It works really well mathematically for us to treat things as ideal gases. And luckily for us, there are some real-world conditions where regular gases, real gases, act like ideal gases. And under conditions where pressure, P, is less than or equal to 1 atmosphere, that's what ATM stands for, or the temperature is greater than or equal to 0 degrees Celsius, which would be 273 kelvins, that is when we're going to see real gases begin to act like ideal gases, which helps us in making predictions and doing calculations. Some conversions that are going to be really handy to know. First of all, pressure. All of these are equivalences, so I can take any one of these and use the ratio to find a conversion for any one that I want it to be in. So let's go down the line. 1 atmosphere, that's what ATM stands for, atmosphere, is equal or equivalent to 760 millimeters of mercury. mmHg is millimeters of mercury, which is equal to 760 torr. Torr is just torr. In which that is also equal to 101.3 kPas. That stands for kilopascals, which is also equal to 14.696 psi, which stands for pounds per square inch. We also need to know some volume conversions. 1 liter is equal to 1 decimeter cubed, which is equal to 1,000 centimeters cubed, which would be the same as 1,000 milliliters. Those we'll see throughout the year when we're dealing with solutions, acids, and bases, and so this especially will be good to memorize. Then when we're dealing with gas laws, we also deal with temperature. Temperature, we have, quite often we measure in kelvins when we're dealing with gas laws because we don't want to have a negative pressure or volume. Those can't exist, and sometimes we have negative degrees Celsius, which would calculate out to be a negative volume or pressure. So whenever we're dealing with gas laws, we want the units to be in kelvins. Kelvins are equal to 273 plus whatever value I have in degrees Celsius. Now, Graham's law. We can have two main things going on with gases. Diffusion of gases is where one gas passes through another gas, like air freshener through the atmosphere. And we can also have effusion of gases, and that's where the gas passes through a small area, like helium gas out of a helium tank into a balloon. Diffusion and effusion are related by the same law, and that law states that the rate of the gas is inversely proportional to the square root of the molecular mass. That's a lot of jargon there, isn't it? Let's look at it in mathematical setup. So the rate of gas A divided by the rate of gas B, so how fast gas A is divided by how fast gas B is equal to the square root of the molar mass of B divided by the square root of the molar mass of A.